the data set, I'm Michael Poston. I'm working with all these fine people here you see on the slide, and I'll be presenting about the thermal stability of adsorbed water molecules on lunar materials. So I probably don't have to tell anyone in this group about the 3 different spacecraft that saw infrared signatures consistent with water and hydroxyl on the lunar surface. But if you're not familiar with that, go ahead and take a look at the papers in Science 2009. There's some great papers. And they've led to a discussion about a possible water cycle on the moon, including origin, different origins for the water, evolution of the water while it's on the moon, and then the eventual fate. Is it lost or is it trapped in the polar regions or subsurface? Today I'll be talking about laboratory experiments that actually have to do with the retention, migration, and trapping of water on the lunar surface itself. So from those science papers, we saw that the band depth varies with latitude, time of day, and mineralogy. So these are 3 things that we'd like to be able to repeat with our laboratory experiments and subsequent modeling. So one surprising thing about seeing the 3 micron signature all over the moon in the high latitudes is that a lot of these places appear to have temperatures higher than 150 Kelvin, which is the temperature where ice will sublime within seconds. So at the upper right, I have a chart from the Diviner website showing just some very macroscopic temperature cycles at various latitudes on the moon. And you can see 150 Kelvin, even the pole in the summer is not predicted to be below 150 Kelvin all the time, with the obvious exceptions of Paul Haynes' recent talk. So what is a possible way that water could actually be retained, molecular water, on the sun that serves the moon at temperatures above 150 Kelvin? Well, chemisorption is a phenomenon where water can actually hold on due to weak chemical bonds, and it will come off at higher temperatures or hold on for longer times than ice can hold on. So the key parameter we need is the desorption activation energy of the site where the water is held. And if you look at this chart over here, this is a temperature cycle with a hypothetical distribution showing that if you have water bound at sites with 0.8 EV desorption activation energy, you'll lose almost all of that at this temperature cycle, which has a maximum temperature of 244 Kelvin. But the 1.0 and the 1.1 EV, you can actually retain almost all of that water for the time scale of this measurement. So the key parameter is to really know the precise desorption activation energy. And the way we get at that is through laboratory experiments in chamber that I've shown schematically on the left-hand side. And basically, we built this chamber to do these temperature-programmed desorption experiments where we cool the sample to a cold temperature where all the water will stick and we can even form ice, in this case about 110 Kelvin. We expose the sample to still a pretty good vacuum, but an elevated pressure of water, and statistically we know how much water has stuck to our sample, and that is measured in Langmuirs. So in all the following charts you'll see this L unit, that's Langmuirs. It's just measuring the exposure of water to the sample. Once we've exposed the water to the sample, we heat at a constant rate of temperature and time and monitor what water desorbs with a quadrupole mass spectrometer. And we compare the desorption rate versus temperature as our actual end product from the experiments. So some theoretical curves to give you an idea of what sort of things you'd expect is if you have ice, you have this purple curve where it all comes off at a pretty low temperature, about 150 Kelvin in the lab. And as you increase exposure, you see that the ice seems to hold on for a little bit longer. The maximum temperature of the peak moves to higher temperature. If you have molecularly chemisorpted water, it's this green curve where as you increase, it just gets a bigger peak but stays at about the same place. And if you have actually hydroxyl OH that can move around and find each other and precombinatively desorb as water, then that'll actually move to lower temperatures as you increase the water exposure. All of these curves were generated with the Pointed-Widmer equation, which will be the same treatment that we use to pull out our desorption activation energies in our actual results. So as a proof of concept, we started out with surrogates, micronized JST1A to represent the lowlands and micronized albite to represent the highlands. And these results have all been published in JGR this year. So we see on both samples we have ice forming, and that state is a sharp peak at about 150 to 200 Kelvin. But we have this broad signal over here at higher temperatures, and that is what we believe is molecularly chemisorped water. You can see this also keeps increasing as we increase the exposure up until, for the JST1A, about 64 Lang meters of exposure, and for the Albite, it just kept increasing and didn't stop even up to 512 Lang meters. So we wanted to get from mature and a laboratory timescale to the actual more fundamental desorption activation energy, and to do that we had to use a distribution function method, which is described in Berry 2008 in Phys Chem Chem Phys, where we basically say, okay, we can't fit this with a single peak, so it's not a single desorption activation energy. Let's consider it to be just a broad, potentially continuous distribution of sites at varying energies, and let's give it a function to describe that. So that function comes out unitless, and to get to an actual cumulative water concentration, which is what everyone was probably more interested in, we had to make some assumptions, including assuming that the entire sample had been exposed to the water that we dosed into the chamber. So taking these assumptions, which are described in more detail in the paper, we determined that for the JST1A we had about 44 ppm of chemisorped water, and for the Albite we had almost 200 ppm. Now these samples had high surface areas compared to the lunar regolith, so once you adjust down to a more lunar-like surface area of 1 meter squared per gram, the concentrations are approximately 8 ppm for the lowlands and 18 ppm for the highlands, which is consistent qualitatively with the spacecraft observation of greater 3 micron band depth in the highlands regions. So with the distribution function of desorption energies at hand, we can then do a simplified model to see what water will persist at various latitudes. And I say persist because this model is only tracking water that has never desorbed. As soon as the water molecule leaves the surface, the model assumes it's gone. So we can only lose water in this model. But we're trying to get an idea of, in this limiting case, where could we have water and what concentrations at these various latitudes. So as you can see, and I should note that the temperatures here are the maximum temperature that the temperature profile we use for that latitude contains. So you can see that we keep a few ppm at basically the pole, and at 60 degrees latitude we're down at the ppb level. So this is much less than what the interpretations of the spacecraft data suggested. But that's okay. We still got a proof of concept, and like I said, these are lower limits. In fact, you've already heard recently, these temperature profiles that we used are pretty simplified. They're from the Savada et al. in 99. So they're a model. They're not the actual temperatures. And as Paul Hain described, there can be a lot of localized cold traps that will be colder than this, but might be still within 1 pixel for M cubed or the other spacecraft. So I'm not too worried about these concentrations being a little bit low. We could also have transiently absorbing migrating waters, such as in the models by Dana in her Kreider and Dondrek papers back in JGR 2000 and following. But I'm sure if Larry Taylor's on the line, so he's saying, but Michael, these are simulants. I want to see something from the real lunar regolith. So we do have some data from our lunar samples that we have. There's some complications in trying to do the lunar samples because they're much lower surface area, which brings down our sensitivity, and they're a lot harder to keep on the sample holder because these are powders, and these larger particle sizes don't stay as well. But we were able to take some data from sample 12001. It's Apollo 12, I want to say low titanium basalt. And what I had to do is I had to take the blank here in purple and subtract it from the saturation value, the orange line for A. Langmuir, and that what you see in the right chart is that blank subtracted saturation result. So then we take that and run it through the same fitting routine that we used in the proof of concept work, and we get this distribution function. Again, it's a cumulative distribution function for the lunar sample. And again, taking the assumption the entire sample is exposed to water, we do see in that limit of 24 ppm as our total chemisorption water. So that's about 3 times as much as we saw from the simulant. But the energy that it holds on at right here is somewhere between 0.8 and 0.9 for the highest energy sites, whereas for the JSC1A and the albite, we were out at about 1.1 to 1.2 for the highest sites. So even though we start out with more water, and at the coldest places we can have more water, we'll lose more to the heating cycles much more easily. So to show that graphically, go ahead, Dana.
2 minutes left.
All right, thanks. So to show that graphically, I ran this through the same fitting routine, or the same water persistence estimate, where I again remind you that as soon as the water molecule desorbs, it's gone in this model. So it is highly simplified. And we see we can actually keep a little bit more water, at least for the first year, at 89 degrees latitude. But as we go to lower latitudes for this temperature model, or for the temperatures used in this model, we lose the water much faster because the higher temperatures do not allow, or do not, because we have the weaker binding sites or desorption activation energies, we can't hold on to as high at temperatures. So again, this is where any migrating water or any water that's produced in situ becomes very important because it could replenish these sites, and that's not shown in this estimate. And this is just to remind us, again, like for example, the orange line on the chart to the left shows we're losing almost all the water because we're sitting here with sites between 0.8 and 0.9, and that's where you can only keep it for a few days at this temperature cycle. So just to conclude and sum up, the lunar surrogates and preliminary results from the Apollo lunar sample support the existence of weak chemisorption sites from molecular water on the lunar surface, even in sunlit locations. These chemisorption sites are capable of retaining water at high latitudes and moderate temperatures during the lunar day. And while the projected concentrations are too low to explain the values reported from the spacecraft observations, less conservative assumptions in the calculations can push the concentrations to higher values. And in fact, the factors that may increase the real concentrations compared to the very simplified water persistence model include these cold traps at the surface or shadowed regions, as Ben talked about in his director's seminar last month. Some replenishment due to transiently absorbed migrating water or in situ formation, such as we'll be talking about, I think, tomorrow. And with that, I can take any questions.
Thank you, Michael.
Hey, Mike.
Michael, I think there was a, Jerry Sanders had a question for you. It was more of a comment, I think is what he said, is that if you're going to use simulant for lunar polar regions, you should not use JSC1A, Lunar Highland type by NASA, and Shinobi by NORCAP might be better since they are anthracite-based and meet lunar particle distribution curves.
Okay, thanks. I think we moved on to the actual Apollo samples at this.
Right. Let me ask you a question. You talk about again. This is Bill Farrell. You talk about these chemi-absorption sites. Aren't these sites more plentiful in situ, where you have impacts and sputtering constantly going on? In some sense, you're looking at sort of almost like the last vestiges of these absorption sites in a sort of a more placid environment. Would you agree with that?
Yes, I definitely agree with that. We would expect in an actual environment and charging situation there might be more sites, but without having done the experiment or doing a detailed model, we can't commit to any one prediction yet.
Right. Let's see. I think here Carl Hibbets has a question.
You know, Billy just asked a question that was on my mind, and, you know, Michael's well aware of it. So also composition and orthosite would be an interesting one to look at, but Mike already knows this. This is a work in progress, and they're making excellent progress on it. But I want to point out that it's very difficult to actually simulate the lunar surface, even when you have lunar samples, because when you get them back to the Earth, they immediately they're passivated. The surfaces become passivated. You have to deal with that fact.
Right.
Right. Even the samples that have been stored in the inert nitrogen atmosphere, there's a small contamination level of water in any gas purge you have. So these samples have all seen some water in the last 30 or
I think Aaron Sense got a question. With dissociative absorption and recombination, which looks stable at high temperatures, help reconcile abundances between your lab data and the spacecraft data?
In the paper, the JGR paper, we took a look at trying to see if there's any of this dissociative absorption where you actually have hydroxyl on the surface rather than water. But then when it heats up, it comes off as water again. We looked for that, and we believe leaving the surrogates. And we haven't done this yet for the lunar sample. But we saw some initial hydroxyl leaving the surrogates, but we weren't able to bring it back by putting water or air or even methanol. You know, we tried a bunch of different things, and we weren't able to bring back those initial hydroxyl groups. So basically, we don't have any evidence right now that we can actually do dissociative absorption on the surrogates. And my understanding is that would also show up more at the 2.8 micron rather than the 3 micron. And that a lot of those concentrations, it's unclear if they're talking about just the 3 micron, just the H2O, or if they're talking about total hydrogen. So does that answer the question?
Hope so. Stephen Wood had a question.